Hello there, it's Keith here, and this is lesson 2 of the Hello World series of my SuperH assembly programming tutorials. We're looking at the 32X today. The 32X is of course a Genesis extension. It's an add-on module to the Genesis or Mega Drive if you're familiar with that name of it. And we're going to be programming it today. Now usually in these tutorials we write a single ASM file that will do the job being to show a simple Hello World message like this one. However, for today's example actually we can't use a single ASM file. The reason for this being, as I say, the 32X is a Mega Drive add-on module, and part of that module is it needs to initialize the Mega Drive itself. So we need a 68,000 program and a 32X program. The 68,000 program is just the initial headers and a passing over of control over to the 32X side for the graphics, and then the 32X side needs to set up the graphics and actually do the example for today. But we can't do this without some kind of Genesis example. Now, because I've always previously used VASM for the 68,000 part, we're going to continue using VASM for that part, and we're going to use ASW for the SH2 part. So 2 files, 2 assemblers, and 1 example. Okay, let's go over to our code and let's see what we've got. Okay, so this is our Mega Drive part that we'd really rather not have, but we've got to have it. So this starts with a exception table. However, this is the legacy exception table, and this basically contains a series of jumps to the 32X startup. So this is what we need to have as our exception table. We've then got our header for our Genesis cartridge. This is some sort of pretty typical. We've had this before in the Genesis tutorials that I've done, but this is the one we've got today. We then have at memory address 200 the new exception table, which is the one which actually is being used now by the Genesis. So we've got only one that we're actually using here. We've got the jump to our program start, and this is the 68,000 program start, the Genesis program start. So that will be executed, and then we've got a series of RTEs for the rest of the exception table. What we then have is the 32X header. So this is the actual 32X program, and there's a few things that are important here. Now we've got a label My 32X program here, which is the start of our ROM cartridge for the 32X side. Now this label actually exists at the bottom of this ASM file, and the reason for that is we're going to binary combine the 2 files, the 68,000 part at the start and then the SuperH part at the end of the binary, and so that label will end up being our binary program, and that is copied into memory on the 32X side by the hardware. Now it will be loaded in at this memory address here, 6 and then lots of zeros there. That is the memory address that the cartridge will be copied into RAM at, and so that is the execution address. Now we're specifying 2 execution addresses because the 32X, among its many difficulties, is it has 2 processors. We're only going to use one of them. So the secondary processor, we're pointing to this memory address here. I think that's 600,000 there, so that's the secondary address. And then the primary CPU, which is actually going to do all the work, is at 600,004 there, so that is the primary CPU address here. We're defining a program length here and a few other things here. So these are all good template values that we can use here. Now beyond that, what we have is the 32X startup. Now for memory address 400 onwards, this is a binary block, and the 32X actually compares this to the contents of its own ROM file, so this has to be 100% identical. There is another 2 lines of the startup which also have to always be this, but those aren't actually ever compared to the ROM file, which is why they're separate here. But this does need to be these values for the init routine to work. Now, once we've done our init, what we've got then is our actual 68,000 program. So what we're doing here is we are loading the value from this address here, and this is the VDP control. And then we're setting the top bit of that 16-bit value and writing it back again. Now this releases the VDP, the graphics hardware, and allows the SH2 to use it. Now in the case of this example, we then just drop into an infinite loop. However, it's important to notice that because of the way that the 32X is split up, we can't actually access much of the regular Genesis sound hardware, which is generally used. The Genesis VDP is also sometimes used for an extra layer on the 32X. That's why if you forget to plug in the extra cable, half your graphics are missing and the games aren't playable. And then the other thing is the joypads. The joypads can't be accessed, to my knowledge, by the 32X directly. So those kind of things you might want in a routine here, and I've got a tutorial I'm planning to do that covers how to use those. But as I say, this is a super minimal example, so the 68,000 side is just completely locked up at that point. Okay, so we'll look at how to assemble that in just a moment, but let's look at our 32x program now, 32x hello world. So this is our minimal 32x example. Now, the origin is at this address here, which is where the cartridge will actually end up being copied to in memory. Now, the first thing we've got here is the CPU2 loop, and it's just an infinite loop here. And the reason that that is at that address is because we specified it in our header. If you remember, our header had these memory addresses here as this is CPU1 and that is CPU's entry address, and so that is what we are now seeing on the other side of the cartridge. So that's CPU2's entry address, CPU1 entry address is at that address there, and what we're going to do is we're actually going to process things. Okay, so what we're doing here is we're loading the address of what's known as the input mask here, and then we are reading in a 16-bit value from that, and what we're doing is we're testing for the top bit here, and we're waiting for the VDP to be released. If you remember, we were releasing it on the 68,000 side, and now the 32X side, the SH2 side, is waiting for that release. Okay, so once that happens, we're now able to start using our screen. So we are going to use this memory address here, 2004100. This is the bitmap mode register. Now what we're going to do is we're going to set the bottom 2 bits here. We're going to write a value of 1 to those bits there, and that is setting the packed mode. Now this is basically a 256 color, nice easy mode to work with. So 1 byte is 1 pixel, and we select 256 colors in a palette. Very nice. Okay, now what we need to do next is we actually need to set up the screen. Now there's a couple of things we need to understand about the 32X. Firstly, when the memory that we write to from our program isn't actually the visible screen. Now what we need to do is we need to do a page flip which swaps the two over, so the buffer we're writing will then swap to the visible buffer. So we've got a page flip function that we'll look at in just a moment to do that. However, there's another tricky thing about the 32X. It uses a line table. This is a table of address pointers that define the memory address that is used to draw each line of the screen. And these can sometimes be used for doing clever things like doubling up the lines. So if you want one line to be double height rather than drawing all the pixels twice, you can just point both lines to the same memory address and things like that. So useful for split screens or reflection effects maybe, but rather annoying if we just want a basic screen. So that's what we've got here is a do line table function which sets up a normal linear screen. We then do a page flip and do the same again to set up the second buffer, because there's 2 buffers that will repeatedly flip over. Okay, we're going to look at the code for those in just a moment. What we then do though is we set up our colors. Now our screen may be on, but we don't have any colors in it, so we need to set some colors up. The memory address is 2004200. That is the palette color RAM. Now there are 2 bytes for each color there, and so we're loading them in from a palette. We've got 4 colors in our palette. We transfer them 16 bits at a time until we've done the entire set of colors, and we can see the colors at the bottom of our code. So if you want to play around, you can do so. So here's our 4 color palette here. So I always use the old Amstrad CPC colors. The Amstrad CPC in 8-bit was 4 colors, so I always define 4 colors for the retro feel there. Now the color palette definition is really simple. I like simple palette definitions. So 5 bits per channel here, and so in that format there, so you can see if you play around in the bits, I'm sure you can get any color you want. Okay, so that is how we set up our palette. Our palette is now ready, and then we are now ready to start actually showing some text to the screen. Now we are actually defining our own character drawing routine. We're drawing pixels straight onto the screen, so we are remembering an X and Y position in characters basically, so that we know where to draw the next character. So what we're doing here is we are just zeroing the X and Y position here. Cursor X and cursor Y are offset within the user RAM, and so we're just writing a 0 to those there. What we're then going to do is we're going to use our print string routine, which we'll see in a moment, to print the hello world message to the screen. So we load the hello world message into our 13 and run print string. Now once we've shown some data, that will have transferred the pixel data within the buffer. However, we then need to flip the buffer onto the visible screen, and we do that with the page flip routine. So that is now flipped the visible buffer onto the screen, and then finally we drop it into an infinite loop. Now if we forget to flip our buffer like so, we get a very boring blue screen, so that's not very good at all. The other thing of course to notice is if we don't define our line tables here, if we disable the line table definition routines, we get a blue screen again, because now we've got no memory pointers to our screen memory. So let's take a look at how we define those line tables and flip that buffer, because these are important things. Okay, so the buffer is at memory address 24 and then 6 zeros. That is the start of VRAM basically. So this table contains 16-bit entries, and these 16-bit entries are the offset in words of the actual memory address. Now this is the actual area of VRAM that we are going to be using, but it's only the bottom 16 bits that we would actually transfer into this table, because we're writing 16-bit values into this table, and we need to divide them by 2. Now we're actually going to start at 24000200. The top 2400 part is omitted, and so we've got the 200 part there, but we're dividing that by 2 and writing values of 100 and onwards in our line table. Now we want to write a total of 224 lines, and each line is 320 pixels, but as I say, we need to divide everything by 2 that we write into this table, so we're going to add 160 for each line. Okay, a little bit complicated, I know, but the good thing is that once we've got this working, we can just forget all about it. So we write our value of this entry in the line table into R6. We then add the 160 to the next address that we're going to write into the line table there. And then we add 2 to the position in the line table. And then we are basically going to repeat until we are done. So we're repeatedly writing entries. So the first one would be 100, and then we would add 160 to that for each line, repeating 224 times, and this produces the line table. Now we're actually doing this twice, once for each buffer, we have to do it twice, and in between those we are using the page flip, and of course we're also using the page flip when we want to actually show the results of our drawing to the screen. Okay, so how does that work? Well, we've got a copy of the VDP status register in our user RAM, so we're loading that previous version here, and then what we're going to do is we are going to actually update the register here at 2000410A. This is the register that controls the buffer flipping. Now it's the bottom bit we want to change here. So what we're going to do is we are going to flip the bottom bit in the value we've stored in our buffer here, in our copy here in the user RAM. So we're flipping the bit there, and then we're writing this back to VDP stat here. So that is updating VDP stat. And so we're writing this back to the hardware register here at 2000410A. But there's a catch, you see, the buffer won't actually flip until the next V blank. And that bit, if we try and read it back, won't have actually changed until that V blank occurs. So what we're doing here is we're reading back the value from the register we just tried to change, and we're comparing it to the value we wrote. You see, we wrote the value here and we're comparing it here and seeing if that bottom bit matches. Now if the bottom bit hasn't flipped yet, then we're just going to wait until it has. Once it has, we then return, and now the visible screen will be the one that we expect. So that's how we actually draw our image to the screen, flip our buffer. Now what we're going to look at now is just the actual data that we've got prepared for this example. So we're aligning here to 32-bit. We've got a literal org, that is for when we're defining literals that are too long for the immediate values there, so that they all end up at LT org. We've got a hello world string here, they're 255 terminated in my examples, that's what I always use. We've got our font, this is the same font I've used in all of my tutorials, even the humble ZX Spectrum. That means that it's a 1-bit per pixel font. It's 8 pixels wide, 8 lines tall for each character. That means there's 8 bytes per character. It's important, we'll need that later on. We've then got our palette, and then we've got 8 longs worth of user RAM, and we're using 3 of those. The first one is the cache of the VDP status register. That's for when we're doing our page flipping, and then the X and Y position of our cursor. Okay, so let's take a look at the print char routine. First we'll look at the print string, I guess. So here's print string, very straightforward. We are loading in a byte from R13, incrementing R13 into R0, comparing that to 255. When we move a byte in, it's sign extended, so we're comparing it to -1, which is the equivalent of 255. If it matches, we're done, so then we would return. If it doesn't match, we run the print char routine, and we just repeat until we get that 255. So all of the dirty work is being done by print char, and this is part of my procedure for creating tutorials on a new system. Get the screen working, draw a byte to the screen. If you can change a single pixel, that's a start. Then print a character, and then I use that print character routine and I build on it to print to do debugging tools and things, which we'll see in just a moment. Okay. So here's the print char routine. The first thing we're doing is we're backing up all the registers we're going to use. This is every register that this routine uses, and this is restoring every register that that routine uses, and that means that this will not cause any harm to anything else that I might be doing. Okay, now the first thing we want to do is work out the source data from our font. So we are loading the address of our font, and then we need to calculate the offset for the character we want to show. The character we want to show will be in R0. Our font has no characters below space, which is character 32, so we're first subtracting 32. Each character in our font uses 8 bytes, and so we're shifting to the left 3 times, which is effectively multiplying by 8. We then add that calculated offset based on the character we want to show to our font. We've now got the source bitmap data in R5, 1 bit per pixel. Okay, very nice. Now, if you remember the line table, we set all of our pointers to be at address 100, and as I said, that is effectively half the actual address. So the actual address will be 200, and that offsets from 24000, and so it's 2400200 is the base of our screen. Okay. So we want to calculate the VRAM destination for this cursor position. So we're loading the cursor position from user RAM. Now our X position, we effectively just need to multiply by 8 because there's 1 byte per pixel and there's 8 bytes per character in width. So we're multiplying our X position by 8 here, and we're adding that to our VRAM base here. We're then taking our Y position, we're multiplying that by 8 because we want this in lines, and then we're going to multiply the line we want by the number of bytes per line. 320 bytes per line, 320 pixels per line as well, which is a coincidence. It's almost as if it's 1 byte per pixel. Of course it actually is, so it's very convenient. So we are multiplying 320 by the line number here, and we're transferring the result of that multiplication, which ends up in the special register MAC-L, into R0, then adding that to R6, and R6 now contains the pixel position of our destination. So we've got our source in R5, our destination in R6, we're ready to go. Well, very nearly anyway. We're going to shift the bits out the right hand side of our source red in byte, and so we're going to draw to the screen from right to left. So we're moving to the last pixel in the character, adding 7 to move to the right hand side of the character. We've got 8 lines of our character. We've got 8 pixels per line, so we're using those 2 counters there. And we're going to move a single byte out of R5 into R3. So R3 contains this line of our character. Okay, now we're going to use R2 to be the color that we're going to draw to the screen. So we're loading 1 into R2, and that is yellow. And then what we're doing is we're shifting a bit out of R3 on the right hand side of our source font byte. And if that is a true, then we're going to skip over the next part. So that would mean we've got a 1 out of that line of our character. Now, if we haven't, then we're going to set our color to 0, which is the background, and then we're going to transfer that byte to the screen. We then move left across the screen because we've drawn a byte to the screen. We then repeat for this line. Once we've done an entire line, we then need to move down a line and move back to the right of this character. So we are effectively doing that by adding 320 plus 8. 320 is the length of the line, 8 to move back for the 8 we've just drawn to the screen. And we're then repeating for the remaining lines of this character, 8 lines for the character. Once we've drawn a character to the screen, we're then moving our X position across. There's no new line. When we get to the end of the line, we would just keep writing forever, which would cause a mess, so don't do that. But we will see a new line routine in just a moment. So that's the end of the example. So all of the dirty work is being done by printchar. We just then extend that into print string, and we use print string to show our hello world. All very straightforward. And of course, if you want 0 termination, you can just change the compare routine here. I always use 255 just for consistency because that's what my ChibiAkumas game used to use. So it's just all passed along from there. Okay, so those are the example ASM files. How do we build them? Well, we build them with 2 scripts. When I press F6 on my build script, which you can get from my website, I have an ASW32X. Now this is assembling the SH2 part for the 32X. I also have a VASM 68000 for the 32X, which compiles the Genesis part. So we're going to take a look at both of those. So this is the first one, VASM 32X. Now a lot of the code here is a little bit overcomplicated. I've got various checks and various other functions. The important part is this line here. So this is assembling the 68000 part. Build file is the source ASM file. It's just called build file because I use a batch file. Check labels means we are checking if a label looks suspiciously like a command, which, for example, if we forget to tab in and when we enter a command, it will look like a label, and so that will warn us. It's almost certainly a mistake. No case disables case sensitivity because I'm a Windows user and I am very sloppy with my case, so not a good thing. We're defining some symbols. I'm defining vasm here and build gen. I use these for conditional compilation if I want to later use a different assembler, but there's some inconsistencies that will help me out. And if I'm assembling for multiple systems, that helps me out. Although I've got build gen there, maybe it should be build 32x. I don't know. I guess maybe this would help me out if I was going to reuse some of my old Genesis code, because as I say, things like the sound, I've used my Chibi sound driver from the Genesis examples on the 32x. It works fine, and that is actually what you would need to do. Anyway, we're outputting a listing file. These are debugging tools, very handy. Shows how the source assembly converted to binary. Often helps you out if you don't understand what's going on. Sometimes the assembler might be optimizing things in a way that is causing you problems. You don't need it, but I'd suggest you get it if you can. And then we're telling vasm to output a binary file, and we are specifying the file is gen.rom. So that's how we build our 68,000 part. What about our SuperH part? Well, we're using a different assembler, but it's roughly the same. We're using ASW here. Again, we've got our source file. We're specifying the SuperH. That is called the SH2 That's the other name for it. It's the same thing though. So that is the processor we're using here. Again, we're specifying a listing file here. Those are the commands for a listing file. We are specifying again a symbol here. Build 32x is defined, and we're specifying that we're going to output a file called prog.build, but that isn't the final binary. We need to do an extra stage on this system to convert to the object file into a binary. We use p2bin, and we pass that file that was just created and convert it to a final binary file. So that converts it to a raw binary. What we gave it is what we end up with, whether that's enough or not. Now the final thing we're doing is we're combining the Genesis ROM at the start of our file with the 32x ROM at the end of our file, and we just use copy with a B switch for binary, and we just do a plus, and that's all we need, and that will create the final binary file. So that is now a working cartridge. So the last thing we do is we run it with our emulator Fusion, and we specify our cartridge on the command line, and it automatically runs it. Very nice of it. So that's very straightforward. Now the last thing we're going to look at very, very quickly is my advanced example. This is basically a template that I use for my tutorials. So this includes my simple developer debugging tools. One shows the contents of the registers to the screen, very helpful if you're getting started and you're testing commands and things. The other one dumps bits of memory to the screen, and also very helpful. So I use these for things like if I'm trying to learn how to work with a joystick, I try and read in the joystick, I show bits of the registers that I've read in to the screen, and if parts of the program's malfunctioning, maybe I dump parts of the addressable memory to see what's going on in depth. So these are really helpful for me, and once I've got my Hello World example, basically they're very easy to get going. So I've included basic macros here because that is used. This is just a push all and a pop all macro to automatically back up and restore all the registers. The monitor uses that. And then finally, we're including the monitor here. It's far too complex to go into here, but that is a software monitor tool. Of course, hardware monitors are going to be more powerful. However, me being multi-platform, working on lots of different systems, lots of different emulators, I have come to adapt to not using them because they're often not available, and on every different system their capabilities and usage is completely different, and it's just too much for me to learn that many of them. I would forget them as fast as I was learning them, so I just use my own software tools now. I've just adapted, and I cope with as little as possible, and what I do require I am able to code myself, which is the way I try and work with things in general. Okay, well, there's one final thing that those monitor tools need though, and that is a new line function. So here it is. All we do is we write the X position to 0 and increment the Y position. Very straightforward. And so that is used at various points in the code. So there we go. So that is all we've got for today. I hope you like what you've seen. If you have, please like and subscribe. This is the start. This is the Hello World series. That's the end of the Hello World series, but there's a follow-on called the Simple series. These are single ASM files again, and they each do a simple task. And so things like reading in the joystick, moving a sprite, drawing a sprite to the screen. One example, one single ASM, one task being done. And the single ASM thing is just basically in case you don't want to use the assemblers I'm using and you need to convert them, because I've done it myself and it's very annoying when you've got 500 different ASM files and all these included files and all of these symbols being defined, and you having to pick the assembly file apart when all you want to do is get a minimal hello world so you can get on with things at your own pace in your own way. And that's what this example was intended for. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.